So this news article caught my eye. Talked about why Europe's healthiest economy has its worst drug problem, and I thought it was going to talk about Germany because I always thought that they had the healthiest economy of all the countries in Europe. And I was surprised to see that they were referring to a very different country here. It's Estonia, and I don't know if you can see with my laser pointer, but up here on the map in red, that's the country of Estonia. So apparently they're doing pretty well, even though Europe is in an economic downturn at the moment. And what the drug problem that they start to talk about here is a drug that they refer to as China White, which is sort of the unofficial name. The actual chemical name for this drug is fentanyl. And it relates to a class of molecules that we've already talked about, and that's opiates. What's amazing about this stuff is that it's anywhere between 100 and 1,000 times stronger than skag, which is heroin. 100 to 1,000 times stronger. So imagine taking a hit of heroin, but something 100 to 1,000 times stronger than that. And I think we can get a sense for why that might be super addictive and a super big problem. Let's take a look at the molecules behind this story. What is skag? Skag is heroin, but of course when heroin gets in the body, there's esters on here, 2 acetate esters here that allow heroin to cross the blood-brain barrier. But importantly, when it gets inside the body, it gets converted into morphine, and that's the drug that binds to mu-opioid receptors in the central nervous system and gives the pleasurable feeling. So this is what ultimately binds to the receptors in the brain. And what's amazing is this very simple, maybe not to you yet, but by the time you get to 51C, this will look like a very simple molecule, fentanyl. You'll know how to make molecules like this just by taking Chem 51C. And the fact that chemists can make something like this and it's 100 to 1,000 times more potent than this molecule that's optimized by nature, I think is pretty extraordinary. So, I mean, the good part about fentanyl is not for as an addictive narcotic, but of course that's a painkiller that's used clinically. Okay, and so you'll have to wait to the amines chapter before we talk more about how to construct molecules of that type, and that's coming up, I think, in chapter 27, I think, in the book, in Chem 51C. Okay, so let's bring ourselves back to chapter 10. And I'll just remind you of where we're at right now in the class. Chapter 10 is about 5 reactions over and over and over again. We're talking about these 5 reactions. And we have now talked about 4 of these 5 reactions. So we're going to spend today finishing up this last reaction. And then I'll talk a little bit about how to approach synthesis problems, multi-step synthesis problems. And then I can just show you a little bit about alkynes. Obviously we can't go very far because you probably didn't download those little lecture pages to write stuff in. But maybe I can just say some general stuff about alkynes. Okay, so chapter 10, 5 reactions. So let me enumerate these because I keep referring to these 5 things. Reaction number 1, one of the first things you covered was the addition of HBr and HCl across alkene double bonds, and it generates carbocations. So the initial protonation of double bonds by HBr and HCl involves a carbocation, so you have to worry about rearrangements. Reaction number 2 that we talked about was hydration of double bonds, the addition of H and OH. I'll draw that H for you. So when you add water across a double bond, you add an H. The initial event is protonation of the double bond, and it generates a carbocation, just like addition of HBr or HCl. So you have to watch out for carbocation rearrangements. So there's 2 reactions of double bonds where you add H and something else across the double bond. The third reaction we talked about was addition of bromine and chlorine across double bonds, Br2 and Cl2. There's no carbocations in this reaction. Remember, you go through this cyclic 3-membered ring bromonium ion. Or if you're adding Cl2 chlorine, then you go through a cyclic 3-membered ring chloronium ion. But there's no carbocations in that. There's this very weird, I'll draw it with, well, let me do it with bromine because this example is bromine. But they go through these cyclic 3-membered rings, so no carbocations there. And then SN2 reaction opens that. The fourth reaction, this is where we left off. I showed you that you could run these Br2 reactions in water. And when you got a sea of water there, it's water that opens that cyclic halonium ion. And so the class of molecules that you get are called halohydrins. This molecule here would be called a bromohydrin. And throughout this last lecture, I kept emphasizing issues of stereochemistry and suggesting to you that you need to pay attention whether species add from the same face, the opposite face. In these last two cases, reactions 3 and 4, the relative disposition of those two groups that you add is anti to each other. So notice how I was so careful to draw the two bromine atoms anti, and plus you get the enantiomer of that. And here when you add Br and OH across a double bond, also leads to anti. And so that's where we are now. So we're going to spend just, we don't have that much left to cover in chapter 10 here. But we're going to finish up talking about this last reaction. It's actually a two-step sequence. And you always, at least for you in this class, you will always use these two steps together. And you always have to enumerate these 1 and 2. Or A and B if you want. Or Arabic numerals 1 and 2. But if you don't enumerate these, if you simply list all the reagents thrown together, that's wrong. We'll count that wrong. Okay, so hydroboration. Gee, that looks deceptively like, let me draw the H there. That looks deceptively like the sulfuric acid and water reaction. And so why would I be asking you to learn a second reaction? And so let's go ahead and talk about what this two-step sequence is about. Okay, so this two-step sequence is called hydroboration-oxidation. Step 1 is hydroboration. Step 2 is oxidation. And here's what happens. If you take this molecule borane, and again, this has a boron atom in there. I'm going to try to direct your attention to it. Well, let me just sketch it out for you. I'll draw you a little miniature periodic table here. Let's walk across the second row of the periodic table. You got lithium and beryllium. You'll never see anything with beryllium. Way over here on the left-hand side of the periodic table. And then in the second row, here's the meat. Boron, carbon, nitrogen. Ooh, thanks. Boron. So lithium and beryllium are over here on the left-hand side of the periodic table. This is the second row. And then you've got boron, carbon, nitrogen, oxygen. And fluorine is a little too wacky for us in this quarter. We won't see a lot of fluorine chemistry. So those are the second row elements. So we're going to talk a little bit about boron chemistry. So you haven't seen anything about that yet so far, I don't think, boron. But it's electropositive. It is more electropositive than carbon. And that's going to make it very strange. Okay, so here's our two-step sequence. When you take an alkene and you add borane, that's this molecule here. Let me just write up above here that that's borane. So if you hear me refer to that, BH3. What happens with this reagent is it adds H and BH2 across that double bond. So where I used to have a double bond, I'm going to add H on the more substituted carbon. And I'm going to add this heteroatom boron on the less substituted carbon. And so that is immediately different from the addition of HCl and HBr. When you added HCl and HBr, the H added to the less substituted carbon. So this gives us a way to achieve the opposite regiochemistry. And then after this next step, step 2 here, you mix hydrogen peroxide and sodium hydroxide together. And you will always use this two-reagent combination when you follow a hydroboration reaction. There's never a time when you don't use that as a pair, at least in the Chem 51 series. So ultimately, at the end, look what we've achieved after this oxidation step. We've replaced, and I'm not going to draw that H there for you anymore. We've replaced the boron with a hydroxy group. And this is the opposite. Overall, it's a hydration, but it's the opposite regiochemistry as sulfuric acid and water. If you had used sulfuric acid and water on this substrate, you would have had the OH at the more substituted position of where that double bond was. Okay, so let's practice here. Here's another alkene. And if I apply this two-step sequence, step 1, I mix in some borane, really reactive stuff. And I'm not going to draw the intermediate. And then step 2, we do this oxidation step with hydrogen peroxide and sodium hydroxide. You can buy those reagents at Albertsons. They sell hydrogen peroxide in brown bottles. They sell lye for cleaning sink clogs, L-Y-E, lye. That's sodium hydroxide. And so remember what I told you. The end result is that you put the hydroxy group at the least substituted position. And I'll draw the H there, even though you don't really have to. And that's the end result. And if you had used sulfuric acid in water, you would have gotten the opposite regiochemistry. So that's powerful. You need to remember this reaction. I'm going to use this on you as a way to test whether you know this way to achieve opposite regiochemistry. Okay, so let's talk about some of the details of this two-step sequence, this hydroboration-oxidation. Oh, here's my little periodic table there. I guess I couldn't resist. Okay, boron. Let's talk about borane, BH3. It is super electrophilic and angry. It's just like carbon. It's a second row atom and it wants 8 electrons. Every second row atom wants 8 electrons. And so if you put borane in some sort of a solution, it is going to pick up electrons from somewhere. And if you have alkenes in there, alkenes will attack boron. So here's boron with its empty p orbital up here. And I'm just going to mix in the colors here so you can see that angry empty p orbital that wants some electron density. So you can imagine boron just hovering over this double bond here. And here comes this alkene. And just like you saw alkene attack other electrophiles, you saw alkenes attack HBr and pick up a proton. You saw alkenes attach Br2 or Cl2. So I hope it's not that surprising that what's going to happen is the alkene is going to take its pair of electrons and add to that boron, which is so lonely and really wants another pair of electrons in order to achieve an octet. Now before I finish, I'm going to draw a step here, but before I do that, I want to show you something that is completely non-obvious to you. And what I'm going to show you that's non-obvious is that at the same time that this double bond is attacking boron, this boron starts to realize that it's picking up a negative charge, and it doesn't want to do that. So it redelivers this hydride group back to the most substituted carbon. And that's totally different from anything that you've seen before. There's two bonds that are forming and 2 bonds that are breaking. We're forming a boron-carbon bond, and we're forming a hydrogen-carbon bond. And we are breaking the CC pi bond and breaking the BH bond. So this is a one-step concerted reaction. Addition of HBr wasn't one step. Addition of Br2 across a double bond wasn't one step. Hydration wasn't one step. This is a one-step concerted process. And you can see because the boron has to approach from either the top face or the bottom face, that means both the H and the B are delivered syn to each other. Doesn't make a difference for this substrate, but we'll see, I think, in a later example how that can make a difference. Okay, let me just sort of parameterize this carbon here. And let me draw that H atom going up. There it is. And here's where I used to have the CC double bond, and now I've got this very strange looking BH2 group. BH2. It's not like any functional group you've ever seen. It looks kind of like bromine, just alphabetically, but it is nothing like bromine. Okay, so it's still a little bit angry, but it's more hindered, and there's other reasons why this is less reactive than the original borane. Hypothetically, this can keep going and adding to more alkenes, but don't worry about that. If I ask you the mechanism, you stop here. So now, this is the initial step. We'll talk about the oxidation in a second. How do you rationalize this? How do you rationalize the fact that the hydride comes back in and adds to the most substituted carbon instead of the least substituted carbon? And what I'll tell you here is, here's the mechanism. This is the mechanism I want you to draw. But how do we rationalize? How to rationalize the regiochemistry? And what I'll tell you is that the transition state, as the boron is getting closer and closer, resembles what I'm going to show you here. The transition state for this reaction resembles this. That as I get closer and closer and closer, as as the boron starts to form a bond, if I pick these electrons up from that double bond, and I form a fourth bond to boron, that boron now has to pick up a negative charge. If I have 4 bonds to boron, it will have a negative charge. I call it a borate whenever you have something with a negative charge. Carboxylic acid with a negative charge, carboxylate, borate, palladate. So we'll see a species very much like this. But when I took the electrons away from this other carbon, I'm going to leave behind a carbocation. And there it is. So in the we're getting to the transition state. As the transition state looks more and more like this, what happens is this carbocation realizes there's this very nucleophilic BH bond here, and that BH bond just attacks it. This is what the transition state resembles. So when you initially add the boron, as you're approaching the transition state, you want to build up carbocation character at the most substituted carbon. That's what's driving the regiochemistry. That's why the H always ends up at the more substituted position, and the boron always ends up on the least substituted position. We call this mode of addition anti-Markovnikov, because the regiochemistry is opposite of those other 4 reactions that I showed you. So this is an anti-Markovnikov mode of addition. And that's when you use boron, when you want to achieve that. Okay, so we got this kind of, to you right now, it's going to seem like a very complex 2-step sequence with borane and then this mix of hydrogen peroxide and sodium hydroxide. But after you've drawn that 50 times, it'll just flow out of your pen really easily. Okay, so let's go ahead and talk about the oxidation of this boron-carbon bond, because there is no case ever on the planet Earth where you, in an organic class like this, would ever isolate that boron compound. Super reactive stuff. So we will always take that intermediate that has a carbon-boron bond and convert it into an alcohol in this class. Okay, so here's an example of this reaction. So notice we've taken an alkene that's differentially substituted. The top carbon has 3 substituent, or I guess 2 substituents on the alkene. And then the bottom one has an H that I didn't draw and 1 alkyl substituent. And so based on what I told you, the H always adds to the most substituted carbon. You should expect the H to add to the top carbon of the alkene. And that's what I've got drawn over here. And then the BH2 group ends up on the bottom carbon, because that's the least substituted. Now we're going to treat this with this special reagent combination, hydrogen peroxide and sodium hydroxide. I have no idea why they... again, what are you really doing here? I don't want you to draw it this way, because then you'll miss half the sapling questions. What you're really doing is you're making a hydroperoxide anion. You're using sodium hydroxide to deprotonate hydrogen peroxide. And the reason you do this is because you can't buy sodium hydroperoxide. You can't buy this. But if you knew that this was the point here, in a graduate class, I would allow you to just write sodium hydroperoxide. So that's really what you're adding. You're not adding 2 different reagents. You're just kind of making it a reagent that you can't actually buy. Okay, so the whole point here is that you're oxidatively cleaving this bond. And here's something that you've never seen before. It's yet another strange part of this reaction. Notice that the boron bond was syn to the H that we initially added. When we do the oxidation, we replace the boron atom. This is nothing like an SN2 reaction or any reaction you have ever seen. Now, the book doesn't show you the mechanism for this oxidative boron carbon bond cleavage, and I'm not going to show it to you. You don't need to know it. If you want, I can show it to you later in secret, but I'm not going to ask that to you. But the point is that this is nothing like SN2. Obviously, it's not anything like SN2, the mechanism for replacing boron with oxygen. You replace boron with retention of stereochemistry. So the net effect is that you add H and OH in a syn fashion. Even though it's a 2-step sequence, the OH and the H always end up syn to each other in the final product. Now there's another product that you would have gotten here, and I didn't draw that, and so I'll go ahead and make a point of that. The other thing you would have gotten here is that you would have also gotten the enantiomer of this intermediate and you would have gotten the enantiomer of this product, plus E. So in case you're wondering, why did the boron only add from the top face and not from the bottom? Yeah, the borane would have added from the bottom face as well, 50-50 chance. Okay, so that's hydroboration-oxidation. Again, it gives you the opposite regiochemistry of a regular hydration reaction. The H ends up at the more substituted carbon, and the mechanism involves this syn addition, a concerted addition of H and BH2 across the double bond. And there's always this second step that involves two reagents. Step number 2, hydrogen peroxide and sodium hydroxide. And that replaces the boron with retention of stereochemistry. It's not an SN2 reaction. I'm not going to show you the mechanism. Let me just write it down there in case you look at these notes later and wonder what's going on with that. I won't show the mechanism. Not that I don't think it's important, but just don't want to add that to all the stuff in the book. Okay. So we're going to finish out this chapter, and I'll show you just one of the main themes towards the end of this chapter. The last two sections of this chapter are basically review. Here's the 5 reactions you learned. But more importantly, it's review in the context of how do you mix this together with reactions from chapters 9 and 8, and even chapter 7. So on the last problem set, I had some problems at the end that were multi-step synthesis. And this here is exactly the way, pretty much, exactly the way I'm going to ask you questions on exams. And the other instructors will do the same. And this will happen again in Chem 51C. So you can expect multi-step syntheses to be an important part of organic chemistry from here on out. So what is multi-step synthesis about? It's about, I give you a starting material, and I give you a product, and you have to figure out what steps and reagents. And it's never going to be one step. I wouldn't ask you that. I'm very clever. I know how to pick reactions that you can't possibly do in one step with stuff that you know. So I ask you, how many different steps and what reagents, actual chemical reagents, would you use in order to synthesize this? That means reagents that come in bottles that you can pour into your reaction. So how do you approach questions like this? So here's how you approach in a question like this. There's 2 different directions to approach this. You can move forward and start looking at the starting material and say, what do I know how to do with that? Or you can look at the product and say, well, how many different reactions do I know that can generate those kinds of functional groups? And so let's try that. If you're on the exam and there's a question that says, gee, how do I take this complex starting material and do this? You have to resist the temptation to try to think of one-step ways to do that. So here's how I would do it. I would start off by saying, okay, let me list every single reaction I know of an alcohol. I look at all the functional groups here, and I'm not going to pay attention to this CH2, because nothing happens to that. I'm not going to pay attention to the bottom CH2. That's still there in the final product. I'm going to pay attention to the parts of this molecule that seem like something has changed. And so I'm going to pay attention to the alcohol. What are all the reactions I know of alcohols? And so I'll start drawing them out. Let's think of some reactions. Well, I know tosyl chloride and pyridine. I love that reaction. That allows me to make OH into a tosylate leaving group. You can see that this is going to depend on how many reactions you know and have memorized and have practiced with. What's another reaction I know of alcohols? Well, I know thionyl chloride, SOCl2, and pyridine. I love that reaction. Oop. Oh, that puts a chlorine there. I notice now I'm already thinking, well, there's a chlorine in my product right there. Unfortunately, that leaves me with this H and no way to functionalize it. So maybe that's the right direction, maybe it's the wrong direction. I know reactions with PBr3. That'll put a bromine there. You know, I'm looking at that and I'm thinking, well, I don't even want a bromine in my final product, so that probably is not leading me off in the right direction, but who knows. I know some dehydration reactions. So here's one, POCl3 and pyridine. So your goal is to try to imagine every single reaction you know, and that eliminates it. POCl3 and pyridine avoids carbocations. Not that that was an important part of this. So here's some reactions I know of an alcohol, and I'm just kind of listing them out. And so maybe for some of you it's obvious that one of these I can convert in a single step to the final product, but maybe you can't see that. Sometimes these involve 3, 4 steps. So if I'm stuck here and I can't immediately see how to convert this into that, or the tosylate into that, then oftentimes I'll now go backwards. Okay, I can't figure out where to go from here, so let me try working backwards. Let me think of every single reaction I know that puts either this chlorine there, or that chlorine, or else both chlorines at once. And so I'm going to start off here. Oh, I see a chlorine atom right there. Maybe I could have made that from this. And if I took this alcohol, maybe it would have helped if I angled that chlorine down like it was here. If I took this alcohol and I treat it with thionyl chloride and pyridine, that would replace this OH with a chlorine atom. Or maybe I had something similar here, maybe, or maybe not so similar. Maybe I had an alkene and I added HCl across that alkene double bond in a Markovnikov fashion. That would give me that. So you have to try to think backwards and think of every single reaction you can that would put one chlorine or the other chlorine. But here's one reaction that's fresh in my mind because we just finished chapter 10 here, or we're finishing up chapter 10, and that is that if I take an alkene and add Cl2 across a double bond, I can add 2 chlorines at the same time. And that's exactly the same thing that I just drew how to make over here. So I've already got an exact 2-step synthesis where, gee, if I take the alcohol and I treat it with POCl3 and pyridine, followed by Cl2, that's it. It's a 2-step synthesis. And there may be 3-step syntheses that you could get to, right? Let's take an example. Let's suppose I took this PBr3 and then I eliminated that. This would be yet another way you could have made it. You could first convert the alcohol into an alkyl bromide and then do an elimination reaction with some kind of alkoxide here. And I'll try to pick a bulky one because I wouldn't want to do SN2 at that center, so I'll pick potassium T-butoxide, O-. And the book likes to draw a T-butoxide like this. So in theory, you could have also done it like this. You make the alkyl bromide, you do an E2 elimination, and then you take that and you treat it with chlorine and it gets you there. There may be longer syntheses. We would count all of those correct as long as each of the individual reactions is efficient. So that's an example of how to approach multi-step synthesis. And you can see how important it is to know lots of reactions. To know lots of reactions and have practiced with lots of reactions. Like, I don't know if it was that obvious to you, this disconnection here, that, gee, I could have made this by adding HCl across that double bond. Okay, let's take one more example just to make sure we get a little bit of extra practice. So that's how you approach these multi-step synthesis problems. Again, there will never be any one-step reagent that allows you to do those kinds of problems. It will always require multiple steps and real chemical reagents, not H+. That's not a real chemical reagent. Usually the wording that I put on problem sets and exams is suggest a series of steps and reagents to efficiently carry out the following transformation. I'm going to write steps here so that it's clear that I'm not asking you a single reagent, that there's no one-step way to do this. And of course, when I'm drawing this out, I don't necessarily have to make it easy for you. I can spin it around a little bit just to freak you out, right? And it's not because I'm being a jerk, but that's just the way, oftentimes when you're looking at how to solve a problem, the problem is not presented in you in exactly the way you memorized. And so you have to be good at orienting molecules, reorienting them in your brain. So obviously, these two carbons here are the same ones from the alkene. And so we're back at this kind of strategy. How do we do this? Maybe you can see right off what you're supposed to do. I know 5 reactions of alkenes, and you do too. We just finished talking about 5 new reactions of alkenes. So immediately, you should be able to sit down and write 5 different things that you could do with that alkene. Of course, when I look at this, before I start drawing out those 5 things, I would tend to look over at the product and say, you know, I only know so far 1 reaction to make epoxides. Well, actually, I know lots, but you only know 1 reaction to make epoxides. So why don't we start that way first? And the reaction that you know for how to make epoxides is to take a halohydrin. And let me use this dark pen here because that's almost invisible, it's so thin. And the reaction that you know for how to make epoxides is to take, and I'll make this clear that it's supposed to be anti, to take some sort of a halohydrin, and it can be hydroxy and bromide or hydroxy and chloride, and to treat that with sodium hydride. That's the only reaction you have so far learned. Sodium hydride deprotonates the alcohol, and then it snaps shut in an SN2 reaction, an intermolecular kind of SN2, to make an epoxide. Well, I'm home free now. Because I started off at the end, because I only knew 1 epoxide reaction, it made more sense to start off at the end. So now it's kind of easy. As I look at this, yeah, I know lots of things that I can do with an alkene, but I can immediately see, gee, there's 1 reagent combination that in a single step will give me this bromohydrin, and that's the addition of Br2 in water. And if you had started working in the forward direction, no problem. Like maybe you just couldn't see where to go, and so you drew all these other things out. Maybe you were really excited about this hydroboration, and this pen is not working for me. And so maybe you started drawing out all 5 reactions, and you started off by saying, well, borane, that's okay if you drew some extra stuff out and didn't use it. That's a way to get an alcohol. At least that puts an oxygen atom on the molecule. But it would leave this other H unsubstituted, and you wouldn't be able to make a ring. So again, you know 5 different reactions, 1, 2, 3, 4, 5. You know, it's helpful before you start drawing all those reactions out to look at both sides of this synthesis, starting material and product, to figure out maybe it's simpler if I work backwards. Okay, so strategically, that's how you should approach these multi-step synthesis problems. Okay. So that's all for chapter 10, and this is what will be on our exam on Friday. Exam on Friday will cover chapters 9 and 10. We have another lecture coming up on 11, and I'm going to say a little bit about Alkynes just to get us prepped for that before we walk away here. But that's the end of the exam material. The exam on Friday will not cover Alkynes. Okay, so let's say something about Alkynes. This is our next... Because always at the beginning of the chapter, there's this sort of general stuff. It's like, here's some cool stuff about alkynes, but most of it is not the kind of questions that I put on my exam, and yet you're still expected to know those things because they give you some background. You know, I just posted these lecture notes online, and so I realized that many of you don't have these things printed out to write some stuff in, and that's okay, because we're not going to do very much here. Okay, so chapter 11, it's this. We've done all this stuff with double bonds. Now we're going to do a bunch of stuff with triple bonds. And it's the same stuff. It's the same stuff we just finished in chapter 10. Same reagents. And the only trick here is that now that there's 2 double bonds in an alkyne functional group. So I'm going to start off by just contrasting some bonding in geometry in alkanes, alkenes, and alkynes. Let me just go ahead and draw out an alkane and just remind you of stuff that I think you may already know. So here would be a prototypical alkane functional group. There's really nothing here to see. What I want you to home in on is the fact that this has sp3 hybridization. So each of the bonds you can think of as being made from 3 parts. The recipe is 3 parts p orbital, 1 part s orbital. And that p character tells me something about basicity and nucleophilicity of electrons. So when you look at the angles in an sp3 hybridized alkane functional group carbon, it's 109.5 degrees. I'll just write 109. The 0.5 won't make any difference there. Maybe that 9 is not well drawn. There we go. And let's contrast that with an alkene carbon. So if you have an alkene, let me draw the bonding arrangement on there. And I'm trying very hard to make these look like nice 102-degree bond angles. All of these bond angles here, and here in green, they're all about 120 degrees. Whoops. So they're all about 120 degrees. And each of the carbons in an alkene was sp2 hybridized. Okay, finally, what this chapter is about, this chapter, you can see what's happening as the angles are getting larger as we increase the amount of S character we throw in here. So there's my alkyne functional group. And now the bond angles for the bonds attached to that carbon are 100, and I hope it's obvious, 180 degrees. There's nothing you couldn't have figured out just by looking at these. So this is sp hybridized carbon, and this is going to be the focus of this chapter. What's happening in general, there's something that's happening that you can't see. Maybe I can just try to distort this so it's freakishly distorted so that you'll remember it. What's happening here with p character is the more p character I use to make these bonds, the longer those bonds are. So if you look at the bonds to an alkane carbon like this, the bonds are long. When I use a little less p character, the bonds get shorter. And then I didn't do a good job here, but the bonds to an sp hybridized carbon are really short. Shorter than the other two. So I'm not doing a good job of really distorting these, but I want you to remember it. So that's why I'm making it so crazy distorted. There we go. So now hopefully it looks like the alkyne on both sides, the single bond and the triple bond. Those bonds are much shorter than the other kinds that we've seen before. And I say much shorter. It's a little shorter, but that little bit of length difference is huge in terms of reactivity. Okay, so what's the implications here for chemistry, as far as that bond, as far as the bond length? Here's the overall sum of what's going to happen. So I want to start off by contrasting an alkene and an alkyne. So let me go ahead and draw out an alkene. And let's just try to imagine, and let me make it look kind of long here. Because again, I want you to try to remember this impact of bond length. So there's my alkene. And then over here I'm going to draw an alkyne. And I'm purposely going to make it look really short. Well, those p orbitals are right next to each other, making a really strong pi bond, a pair of really strong pi bonds. Versus my alkene, and the carbons are like a mile away from each other, and the p orbitals are trying to reach over, and they're just not quite reaching all the way over. Okay, so let's imagine some sort of electrophile comes close to each one of these pi systems. So here I'll draw an HX, doesn't matter what X is, could be bromide or chloride. And let's just imagine what we should expect as this alkene attacks that electrophile. And it could be Br2, it could be borane. Because this bond down here, because this alkene bond is longer, what that means is that because this bond is longer, the pi electrons, the pi bond is not as strong. And what that means is that the pi bond is more reactive. It's intrinsically more nucleophilic and basic. And that's an effective bond length. Nothing more, you don't need to know anything more than bond length to know that. So now let's contrast that with these pi electrons that are in this very nice pi bond. You know, the bond's just the right length here. The p orbitals are just overlapping and making a super stable pi bond. And let me dangle the same electrophile above this alkyne pi bond. And let's imagine that coming in and attacking. And I'm going to show you, yes, we're going to add all the same electrophiles to an alkyne pi bond. But the end result of this shorter bond, whoops, I meant to draw that in green. This is a shorter pi bond. Let me draw pi, longer pi bond. And because it's a shorter pi bond, it is less nucleophilic and less basic. So that's the effective bond length. All you needed to know is that the bond lengths are different, and you could have predicted. So that's one effect of the alkyne. Now let's take a completely contrasting effect. Let me go ahead and draw out an alkene kind of edge on so we can try to imagine what's it like for an electrophile that has to approach this. With an alkene, there is a top face and a bottom face to every alkene. Nothing attacks from the side where the alkyl groups are sticking out. It's either top face or bottom face, and those are the only two choices. So let me label those two faces. Things can attack from the top, so the double bond adds its electrons, or things can come in from the bottom. And that's it. We've got choice number 1 and choice number 2. But now let me try to contrast that with an alkyne. And I'm going to try to make this look really wacky and three-dimensional here. Like it's really coming out of the board at us. There we go. Wow, look at that. So stylish. It's like 3D glasses. The whole point here is that with an alkyne, and this is hard to imagine, it's like a cylinder of electron density. Electrophiles can approach from every single possible orientation from an alkyne. You can attack from the side, the other side, the top, the bottom, this quadrant over here. You can attack over here. There's no limit onto the orientations at which you can attack an alkyne double bond or triple bond, or which you can attack a pi bond of an alkyne. So there is no top or bottom. You can attack from all directions. And I hope that you can see, in addition to that, there's fewer substituents on the carbons of an alkyne. Alkenes have 2 substituents on each carbon. Alkynes have only 1. So intrinsically, an alkyne is less hindered. And so how does this math add up? Okay, on the one hand up here I told you that alkyne triple bonds are less reactive because the bond is short. But then down below I tell you, oh, but it's less hindered and more accessible. Less react, so the pi bonds themselves are less reactive, but the overall functional group is less hindered. So as a result, those kind of counteract each other. As a result, CC double bonds, CC pi bonds, are about as reactive as CC triple bonds. This symbol up here was something happened with my font. That's supposed to be a triple bond up there. CC triple bonds. So this confluence of 2 contrasting effects. Alkenes have more nucleophilic pi but are more hindered. Alkynes have less nucleophilic pi bonds but are less hindered. So as a result of that, you have about the same reactivity. So that's why all the same reactions we just showed you in Chapter 5, we're getting ready to do all those reactions with alkynes. And there's going to be some subtle differences because obviously if we take the electrons away from one of these carbons, we're going to leave behind a very strange looking carbocation. But this is what we're going to be doing starting on Wednesday's lecture. I'm going to start running you through the same set of 5 reactions. Okay, so again, remember, we have an exam on Friday, and you need to be studying like crazy. Hopefully you were doing that this weekend, studying like crazy. The problem set, sapling homework problem set for Chapter 10 is due tonight, because we just finished our lecture on Chapter 10. So make sure you finish that, and we'll see you guys Wednesday.